Hello, welcome to our swamp cooler assembly presentation. My name is Zane Steinler, and I'm a mechanical engineering junior.
I'm Ryan Binham, a mechanical engineering senior.
I'm Paul Hickerson. I'm a mechanical engineering junior.
I'm Luis Guerrero. I'm a mechanical engineering junior.
My name is Miles Abril, and I'm a mechanical engineering junior.
My name is Jacobo Castillo. I'm a mechanical engineering junior.
All right, for our problem statement, we aim to design and construct a portable swamp cooler using accessible hardware and 3D printed components in order to apply and validate fundamental concepts from heat transfer, fluid mechanics, and thermodynamics through a hands-on engineering approach.
The project was to test concepts we learned from school in thermodynamics, fluid mechanics, and heat transfer, and we wanted to apply this to a real-world system. Some of the technical skills we had to use were hand tools, 3D printing software such as Bamboo Slicer, and CAD software such as SolidWorks and AutoCAD. We also needed to focus on project management, collaboration, and documentation. This allowed us to stay on task and finish everything at a timely manner.
So these are the additional goals and information about the project. The project spanned from June 1st till August 10th. The total budget that we went with was $350. We would meet on a weekly basis. All of our materials were sourced from Home Depot, and our 3D printed materials were made out of PLA plastic.
All right, so our methodology and approach for our first step, we went with brainstorming, in which our teams met up and involved researching, whiteboarding, and coming up with different alternative designs. For our preliminary concepts, we started with a plastic bin with cooling pads and a fan setup we used to test our water cooling capabilities. For our initial build, we started sourcing our materials that would be used in our final design. For example, finding fans with a high CFM, a Home Depot bucket, and a lid setup instead of our bin. For our two-part system build, we went with an evaporative cooling build and a separate dry air setup. Eventually, we ended up merging the two together to maximize our efficiency. And for our final step, which was testing and data collection, we recorded temperatures, values of water, air, and our radiator in 3 different scenarios to test the efficiency of the swamp cooler.
So as you can see on the left, that is our first prototype. This was initially designed to test and make sure that the project was a feasible idea. We had to make our own pad from scratch using cardboard, but in our future designs, we went with a store-bought pad. This allowed for an easier setup. We also didn't have an irrigation system to keep the pad wet, so in our future design, we added a pump and irrigation system to keep everything wet.
On the right, we can see a preliminary design sketch that I came up with. Eventually, we kind of just use this as like a guideline for our design, and yeah.
So this was the final design that we made, just like Miles was talking about in the previous slide. You can see the store-bought cooling pads that are in there, as well as the irrigation lines that were used. You can also see the 2 water pumps that we had. On the top right picture, the 2 black boxes in the bottom. And then we had the radiator system that we built that was not part of the original prototype. That's used to push out cold dry air rather than cold humid air that's pushed out by the swamp cooler. We also built a 3D printed shroud so that the fan would be able to fit onto the water bucket. And that's about it.
So for our problems and solutions tab, we had a lot of issues along the way, and we brainstormed some solutions that we were able to apply to the project. The first issue we ran into was our 11-inch fan would not fit to the Home Depot bucket. So we 3D printed a 4-part assembly to align the bucket to the fan. In the top right, you could see it, and on the far right-hand side, you could see this 4-part assembly in action. We also had warping issues due to the heat and the hot glue. So we switched to a plastic bonder epoxy, and that held our design together. If we were to redo this design, we would have used PETG or ABS because the heat warped the materials you could see on the right-hand side, and that material would have prevented that from going further. In the very bottom photo, you can see that we have 2 water pumps. Initially, we had 1 water pump pumping through the white irrigation ring and the radiator, but it was not powerful enough, so we included a second water pump.
This is my pad holder design for the bucket. The first problem we ran into was mounting the pad to the bucket. I initially went through and measured the top and bottom of the bucket to figure out the angle of the wall. Then I had to design a mount for the actual wall itself. Another issue that I ran into was the pad was getting heavy due to the water intake. So I had to add some supports to the bottom of the pad holder. The next problem I ran into was running the irrigation line from the bottom of the bucket to the top of the bucket. I had to implement a hole in the middle of the design, the same size as the irrigation piping, to allow for an easy run-through system for the drip system.
All right, and for the fan adapter, this is the adapter that would make our 11-inch diameter fan fit with a Home Depot bucket lid. And the way that I designed this was by measuring the overall diameter of the fan, which ended up being like 13 or so inches. And then also using the bottom dimension, kind of finding that angle and adding some curvature that way that the fan can sit in there comfortably. Another design consideration is if you look at the top left of that cut sheet, you can kind of see like some little slits in the bottom of that piece. And that was just to allow the fitment of the top of the bucket, and it kind of like would lock into place. And an overall design consideration for this was just the tolerances. I didn't really want any air inputs other than the cooling pad. That way we could maximize our cooling efficiency. So, but yeah, overall, this design worked and was effective. And this is a drawing that I came up with in AutoCAD just to give another, perspective. But as you can see, we've got our adapter. An interesting thing is that you can see the plumbing for each of the water pumps. Like Miles previously pointed out, it was ran through his adapter or his, inner bucket piece. But just for illustration purposes, you can see how the water pump 2 is feeding the irrigation line, which drips onto our cooling pad. Once that water is done falling through the pad, it dips back into the bucket. And then water pump 1 is the one that feeds the inlet to the radiator. Once the water goes through that radiator, it comes out the outlet, and it goes back into the bucket reservoir. Important design considerations were the flow of the pumps. We didn't want that big of a radiator that it wouldn't be able to push water through it. But also, we had to consider the size of our fans being sandwiched together. Also, there is like a max level of water that you can put into the bucket before it starts to spill out. So, but yeah. And then for experiments, we're running them at 95 degrees Fahrenheit. And for experiment 1, it was the whole purpose of it was just to give like a baseline for a system. So each experiment was ran at 10 minutes. Experiment 1 is ran with the evaporative cooling setup and the dry air radiator, or dry air and radiator setup. Experiment 2 was just with the evaporative cooling only. So with this, we expected to see some lower water temps just because the heat input from the radiator was eliminated. And then experiment 3 was to see how much heat gain we would experience once that radiator was then turned on, once the water was at its lowest temperature.
And to piggyback on what Ryan was saying, we managed to get the data for each of these experiments. And on the first graph, we were monitoring the radiator fins, the dry air, and the cooling fluid, or the water here. And what the graphs show were a overall downward trend over time as expected. And for each slope, we were able to see that the fins were able to cool the fastest at first initially. Water cools steadily over time, and air was kind of like the last to cool down, or those longest to cool over time. And why are these slopes different? Mainly because they have different thermal masses, conductivity, and convection. Implications for this experiment kind of show that water is the most effective way to transport heat. The fins kind of excel at spreading heat to the air quickly, but don't store much heat. And air is kind of like the bottleneck for the ultimate heat rejection. Overall, I think the first experiment kind of shows that water provides the best overall heat transfer capability, as well as the fins are able to rapidly transfer to the air, and the air kind of limits how fast the entire system can dump the heat. Now, for the second graph, we decided to not test or not have the radiator system on, meaning we turned off the pump, the fans, and disabled the radiator loop. By doing this, we managed to get the lowest water temperature achieved in this type of configuration. And the reason as to why is because with the loop off, we are removing a major heat input, meaning that warm ambient air is no longer being added to heat through the radiator or convection path. And the evaporative pad still is removing heat via evaporation, so there is no net heat in for water when it drops further. The trade-off is that we are going to get more humid air and no dry, cold air. So we're only just going to get humid, cold, humid air. As for graph 3, we were measuring how fast the water was warming up after turning on the dry air loop and verify that that water is heating up. And with this turning on, we were able to find that the water temperatures rise quickly after startup, as well as the outlet air drops below ambient but stays above water to try to find sort of a middle ground. And the reason why is because it's convection through the radiator, meaning the heat lost by the air is heat gained by water. And yeah.
So this is the breakdown of our budget and bill of materials. As stated in the goals of the project, we did stay below our budget of $350 as our grand total is $336.07. You can also see all of the materials that were sourced from Home Depot in the items list as well.
Through the development and testing of 2 prototypes, we identified the importance of cooling the water before it entered the system rather than recycling warm water. Implementing this change allowed us to successfully complete the project. Overall, this work was both engaging and challenging as it required us to apply practical problem solving to installation and cooling methods. In the end, we were able to construct a functional swamp cooler and gain valuable experience in the design and prototyping process. And then this slide and the next one, beautiful pictures taken by me. Thank you for watching.